Hello everyone. Today we are going to discuss cylindrical capacitor and we are going to find mathematical expression for capacitance in case of cylindrical capacitor. Cylindrical capacitor consists of central cylinder or wire, okay, and concentric cylindrical cell, okay. So we find in this figure, okay, there is central cylinder and concentric cylindrical cell. So I'm drawing over here, okay. So this is central cylinder, okay. And there is concentric cylindrical cell. So we have this, okay. And let us draw an axis, okay. So I'm drawing an axis. So this is central cylinder or wire, and this is cylindrical cell, and let A be the radius, okay. So I'm writing over here, A be the radius of central cylinder. Now the cylindrical cell, okay, has some thickness, okay. So this is a cylindrical cell, it has some thickness, and we take the inner radius, okay, of the cylindrical cell and let B be the radius, that is inner radius, okay. So I'm writing over here, inner radius of the cylindrical cell. So we have this, and let L be the length of the cylindrical capacitor. So we can see in figure 1, okay, we have a central cylinder, okay, and we have a cylindrical cell, and they are concentric, okay, and A is the radius of central cylinder and small b is the radius of cylindrical cell, and L is the length of the cylinder. So we have this. Clear? Now let plus Q be the charge on central cylinder. Central cylinder is positively charged, okay, and let minus Q, okay, be the charge on cylindrical cell. That is, the cylindrical cell and central cylinder contains equal amount of charge in magnitude but opposite in nature or sign. So we have this. So let me erase this, okay. So this is central cylinder, okay. Let me draw this, okay. So this is central cylinder containing positive charge, and the inner surface of okay, the cylindrical cell contains equal amount of negative charge. So we have this, okay. So we have this. So what we find, electric field is directed, okay, from positive towards negative. So we can see electric field is directed from central cylinder towards cylindrical cell. So we have this, okay. Now, as I said earlier, A is the radius, okay, of central cylinder, and B is the inner radius of the cylindrical cell. Now, we assume that the length, okay, let us assume that the length of capacitor L is very, very greater in comparison to B or A. So this is the condition, okay, or this is the assumption. Now, if we have this, then there is no age effect, okay. So we get this. So we need to note this, okay. So we are assuming this. So if we have this condition, then there is no age effect, and electric field will be perpendicular, okay, to the axis. So this is to be noted, okay, and depends only on the perpendicular distance. Clear? It depends only on the perpendicular distance from the axis of the conductor. So we have this, okay, and what we find is that there will be flux only through the cylindrical part of the Gaussian surface. So we find that. So we need to draw Gaussian surface. So I'm drawing Gaussian surface, okay. I'm drawing Gaussian surface. So let us draw a Gaussian surface. We can see in figure 1, okay. So I'm drawing a Gaussian surface, and let R be the radius of the Gaussian surface, okay. So I'm drawing Gaussian surface of radius R and length L. So we can see it from figure 1 also. Clear? So this is B, okay. So we have this. So let us come to this figure. So we have a Gaussian surface, okay. So this is Gaussian surface, okay, having radius R. Now we can see the Gaussian surface, okay, this Gaussian surface of radius R and length L is enclosing, okay, is enclosing charge plus Q. So we have this. So as I said earlier, what we find, okay, if we assume this, so I'm writing over here. So the flux, okay, that is electric flux passes or cross, okay, through the cylindrical surface of Gaussian surface. And we need to note that this Gaussian surface is closed at both the end. Clear? The Gaussian surface is closed at both the end. So what we find? No flux, that is electric flux, passes through the end caps of the Gaussian surface. Here, electric field lines passes through the cylindrical surface of the Gaussian surface. So there is no crossing of electric field lines or electric flux through the end cap. So this is to be noted, okay? So as I said earlier, in order to find the capacitance, we use the concept of Gauss law and potential difference, okay, between the central cylinder and cylindrical cell. Okay, so we need to understand this. Now we can see in figure second, okay, electric field lines, they are starting from positive charge and they are terminating on the negative charge. That is, they are starting from the central cylinder and they are moving towards the cylindrical cell. So we have this. Okay. Now, as I said earlier, we use Gauss law, okay? And Gauss law gives the relation, or it relates electric field, okay, with the charge inside the Gaussian surface. So from Gauss law, we can write electric flux equals surface integral of electric field, okay? Surface integral of electric field throughout the closed surface equals 1 by epsilon 0 times the charge inside the Gaussian surface. So we have this. So let us come to the figure second once again, okay? So we have this. So I'm drawing a magnified diagram, okay? So we have central cylinder and we have cylindrical cell. Okay, so I'm drawing in this way. Now we have a Gaussian surface, okay, of radius r, and A is the area, radius of the central cylinder, and B is the inner radius, okay, of the cylindrical cell. Now we can see, okay, so let me draw this, okay, first. So we have, so let me draw in this way. So these are electric field lines, okay. So we have this. So this is Gaussian surface and is enclosing, okay, enclosing charge plus Q. So we have this. Now let us take this side, okay, or this part of the equation. So if we look into the Gaussian surface, okay, so we have this. This is Gaussian surface. Okay, this is the Gaussian surface. So electric field is leaving the Gaussian surface, okay, or electric flux, they are crossing the Gaussian surface. Okay, electric field, they are crossing the Gaussian surface. So we have this. Clear? We have this. Now let us take a small elementary area, okay, small elementary area, small elementary area. Let's say the magnitude of this area is dA, because we are going to find or simplify the left hand side of this equation, okay. Now what we find, we can express area in terms of vector. So in order to express area as a vector, we need to draw a unit normal, okay, on the area. So let n cap be the unit normal drawn on this elementary area, and unit normal gives the direction of vector area, that is dA. So what we find, vector area, that is dA or vector dA, and electric field, they are acting along same direction. So we find this for every point on this Gaussian surface where electric field and area vector, okay, they are parallel to each other. So we find this, okay, So we find this electric field and area vector. So they are parallel to each other. So from this expression, okay, we can write integration throughout the closed surface E dA cos 0 degree. Why? Because electric field is parallel to area vector. Clear? So we find this. So this equals Q by epsilon 0, because charge inside the Gaussian surface is Q in magnitude. Okay. So we know electric field is constant. Okay. On each point on the Gaussian surface. So we can take electric field out of the integral. So we have this. So we get this. Now we are taking a small elementary area of a Gaussian surface. So if we integrate this, then we get total area of the Gaussian surface. And keep in mind, our Gaussian surface is cylindrical. Okay. So we have a cylindrical Gaussian surface of radius r and length l. So this integration gives twice pi rl. Okay, that is area of the cylinder. So we have this. So we can write E equals Q by twice pi epsilon 0 LR. So we have this. So this is electric field. Okay, this is the electric field between the cylindrical cell and central cylinder. Okay, and electric field is directed from the central cylinder towards the cylindrical cell. So we need to understand this. Clear? And we have free space between the cylindrical cell and central cylinder. Clear? So we have this. So I'm erasing this. Okay. So let's call it equation 1. Okay. Now, as I said earlier, we need to find potential difference between the central cylinder and the cylindrical cell. And we know potential difference. Okay. That is expression for potential difference. PD is given by Vf minus Vi, where I denotes initial and F denotes final. So this equals minus, and we have integration. Okay. So we are going to integrate from initial to final E dot, okay, dl. So this is in vector. Okay, we have this. So this is a general expression for potential difference. Now we are going to use this expression for finding potential difference. Okay, and cylindrical cell and central cylinder acts as the plates of the capacitor. So we are going to find potential difference between the plates of the cylindrical capacitor using this expression. And let us denote this difference by V. Okay, so this is potential difference between the two plates of the cylindrical capacitor. So we can write in this way, this is minus, and we have I. Now, I is the initial position. Now, we want to integrate, okay? And if you say in this diagram, okay? So we have this. So I'm drawing electric field, okay? And this is negative charge, okay? So we have negative charge. Now let us integrate along this direction, okay? Let us integrate along this direction. This is the direction of integration. So we have this. We are integrating from cylindrical cell to the central cylinder. So we want to integrate along this direction, that is from negative towards positive. Clear? And always keep in mind potential, okay? Potential. So I'm writing in this way, potential of central cylinder is greater than potential of cylindrical cell. So for that reason, okay, we integrate from negative towards positive. That is, we integrate from low potential to high potential. So I is replaced by minus and F is replaced by plus. So we have this. Now, since electric field is directed, okay, directed along this direction, okay, it is directed along this direction, or we can understand in this way, we have positive charge, okay, and electric field is directed along this direction, and we have negative charge over here. So this is the negative charge, okay. So I'm drawing negative charge, and we want to integrate along this direction, okay. We want to integrate along this direction. So this is the direction, okay. So this is the direction of integration. So what we find? So let dl be the small length along this direction, okay. This is displacement along the direction of integration. So we find angle between electric field and displacement is 180 degree. That is, they are directed opposite. So we can write, okay, this as E dl cos 180 degree. So we get this. Clear? Because we are integrating opposite to electric field. So dl is the displacement along the direction of integration. So for that reason, we get this as minus integration from minus 2 plus E dl. So we have this. So finally we can write, okay, potential difference V equals integration from minus to plus, okay, E dl, and let us call it equation 2. So we have this. Clear? Now I'm erasing this, okay. Now from 1 and 2 we can write potential difference V equals integration from minus to plus, okay. So electric field is Q divided by 2 pi epsilon 0 or epsilon naught L, and we have R, okay, and we have dl. So we have this. Clear? Now we can take Q by 2 pi epsilon 0 or epsilon naught L, which is length of the cylindrical capacitor and is constant, out of the integral, and we can write in this way, okay. Clear? So we can write and we have R at the denominator also, okay. So we can write this expression as, now what we find, okay, the inner radius, clear, the inner radius, because we are integrating from cylindrical cell, okay, which contains negative charge on its inner surface, to the central cylinder. That is, we are integrating from this point to this point, okay. We are integrating from this point to, that is from inner surface to the outer surface, okay, outer surface, okay, from here to here we are integrating from inner to outer. Okay, so we are integrating along that direction. So what we find now, this negative is replaced by B, okay, which is the radius, and positive is replaced by A, and we have dl by R. So we are getting this. Clear? Now if you look into this figure, okay, if you look into this figure, what we find, we have Gaussian surface of radius R. Here we have Gaussian surface of radius R. Now let me erase this, okay. So this is Gaussian surface, okay? This is Gaussian surface. And radius of Gaussian surface is R. Clear? It is R. And we are integrating from B to A. Okay, we are integrating from B to A. So this is to be noted, okay? The lower limit is B and the upper limit is A. Now, as I said earlier, we are integrating along this direction, okay? We are integrating along this direction. So this is the direction of integration. Let's say this is the central cylinder, okay? So I'm denoting it by positive charge, and this is cylindrical cell having equal amount of negative charge, okay? So we have this. So I'm denoting in this way. So what we find, okay, if we take a small length, okay, let's say this is DL, okay? This is DL length. We are moving along this direction. I'm taking in magnitude, okay? So we have small length or small displacement, okay? I'm taking small displacement along the direction of integration. Now, we need to write this DL in terms of dr. We need to write DL in terms of dr because we want to integrate this expression, okay? We want to integrate this expression. So we have this. We can see, we can write in this way, V equals Q by 2 pi epsilon 0 L, and we have integration, and the lower limit is B and the upper limit is A dl by R. So we have to express dl in terms of dr. We have to express dl in terms of dr because R is directed outward. Clear? R is directed outward and dl is directed inward. So let us take a small element dr which is equal in magnitude, okay, which is equal in magnitude to dl but in opposite direction. So we take this, okay, in order to simplify this expression, okay, we use this concept. So this is to be noted, okay? So let me erase this, okay? So we use this dl equals minus dr. Therefore, we can write V equals minus Q by 2 pi epsilon 0 L integration from B to A dr by R. So we are using this, okay? Clear? So we have this. Now we can write V equals minus Q by 2 pi epsilon 0 L, and this gives us natural log. Okay, so we have this, so we can write ln R, and limit of integration is from B to A. So we can write V equals minus Q by 2 pi epsilon 0 L, and we have ln, okay, A minus ln B. Okay, so we can write in this way, or let me write in this way. Okay, so we have this. So on simplifying, we can write Q by 2 pi epsilon 0 L ln B minus ln A, and we use the property of log, and finally write V equals, that is potential difference, so we write in this way, okay, by using the property of log. Clear? So this is the expression for potential difference between central cylinder and cylindrical cell, that is two plates of the cylindrical capacitor. Now so I'm writing equation 3 here, okay. V equals Q by 2 pi epsilon 0 L, and we have natural log, okay. So I'm writing ln B by A. So let's call it equation 3. Now we can also rewrite equation 3 in terms of linear charge density of the central cylinder, because positive charges are present on the central cylinder, okay. So I'm writing in this way, okay. So let lambda be the linear charge density of central cylinder. So this equals Q by L. So we have this. Clear? So equation 3 becomes, okay, V equals lambda by 2 pi epsilon 0 ln B by A. So we have this. Clear? We have this. Now we are going to find capacitance of cylindrical capacitor, and we know Q equals C times V. So therefore capacitance C equals Q by V. Now we are going to put the value of potential difference from equation 3, okay, and this equation. So we can write C equals Q by V, and V is Q by 2 pi epsilon 0 L, and we have ln B by A. So we have this. So this cancels out. So we get C, that is capacitance of cylindrical capacitor equals 2 pi epsilon 0 L divided by ln, okay, B by A. So this is the expression, okay, mathematical expression of capacitance of cylindrical capacitor. So we have this. Now we can see from this expression, okay, we can see. So let me write over here. So we have capacitance, okay, C equals 2 pi epsilon 0 L divided by ln B by A. So we have this for cylindrical capacitor, okay, this is for cylindrical capacitor. Now we can see, okay, from this expression, okay, we can see from this expression that capacitance, okay, we can see capacitance is proportional to length of the capacitor, okay, and as the value, okay, of A approaches, okay, approaches B, that is when A approaches B. Clear? So we have this, the capacitance increases. So we need to understand this. So why this happens? Let us understand this, okay? So we can see capacitance is depending on length, okay, directly. And as I just said, as the value of A, that is radius of central cylinder, approaches or is very close to the radius, that is inner radius of the cylindrical cell, then the capacitance increases. So to understand this, okay, understand this, let us fix outer radius B. So I'm calling it outer radius, okay, just to understand more easily, okay. It is actually the inner radius of the cylindrical cell. Clear? And given potential difference between the plates. So we have this. Clear? So we have this. So this is the condition. Now, what we find, okay, as A increases as A increases, from the expression, okay, we have this expression V equals lambda by 2 pi epsilon 0 ln B by A. So what we find from this expression, lambda must increase. Why? Because ln B by A decreases. So you need to note this. So what we find, as A increases, okay, lambda must increase because this decreases. So we can tell that greater the value of lambda, okay. So greater lambda, value of lambda, mean that total charge stored, okay, for a given PD increases. So lambda, the value of lambda is high. So greater lambda, so we can write in this way. That is capacitance, okay, increases. So greater value of lambda mean that total charge stored for a given potential difference increases, that is capacitance of the capacitor increases.